Thank you for attending my session. I'll introduce Xbyak aarch64 just-in-time assembler for Armv8 architecture and scalable vector extension. My name is Kentaro Kawakami. I'm working for Fujitsu Labo, Japan. I'm working on research and development of AI software running on the supercomputer Fugaku for the last 2 years. Fugaku is the world's first supercomputer which uses the ARM instruction set CPU. Here is the table of contents. Firstly, I'll introduce what is Xbyak aarch64, what is a just-in-time assembler. And I'll show you some sample programs of Xbyak aarch. Secondly, I'll show you the requirement for using Xbyak aarch. Thirdly, I'll explain how to write programs with Xbyak aarch. And then I'll discuss how to debug Xbyak aarch programs. Lastly, I'll summarize this talk. What is Xbyak aarch64? Xbyak aarch is a just-in-time assembler for ARM instruction set, which is written in standard C++. The just-in-time assembler can generate machine instruction sequence at runtime. The generated machine instruction sequence can be used as a function from your program. The first JIT assembler was developed for Intel CPU by Shigeo Mitsunari of Cyborgs Labo, Japan. Based on the concept of the original Xbyak, Xbyak aarch is developed for ARM instruction set. This page shows the minimal sample code which uses Xbyak aarch. The red bold text stands for Xbyak aarch functions, classes, and instances. If you want to use Xbyak aarch, include the header file and define your own class inheriting code generator class and implement instruction sequence you want to do. If you make an instance of your code generator class, the machine instruction sequence you defined are written in memory at runtime. The getCode function returns the entry address of generated instruction sequence, so the variable f can be used as a function pointer. Your program can freely call it as a function. In the constructor function of this sample, there are the add function and the ret function. We call these functions as the mnemonic functions. The function name is one of the mnemonic of ARM instruction set. Each function writes a single machine code on the memory corresponding to the function name, such as add, sub, load register, store register, return, and so on. And the function's arguments indicates the instruction operands. Here, 00 and 11 stand for 32-bit general purpose registers on ARM CPU. ARM instruction set includes about 1,000 mnemonics, and each mnemonic can be followed by various types of operands. For example, the mnemonic add can be combined with 32-bit general purpose registers, 64-bit general purpose registers, HMD registers, and SVE registers. The mnemonic function of Xbyak aarch supports all of them. We can generate any machine codes using all the instructions supported by ARM CPU. I think the JIT assembler has two major advantages compared to the existing assembler. The first advantage is that JIT assembler makes it easier to write instruction level code. Since Xbyak is implemented in C++, we can write our instruction level code in C++. The left side sample has two C++ lines. These two lines generate 15 FMLA machine instructions. But if we use the existing assembler or inline assembler, we have to write 15 lines at least. Not only the for loop, but we can combine other C++ syntax to construct machine code sequence efficiently. The right side shows the dynamical instruction selection. Here, we consider division, R1 over the param. The R1 register has the dividend number, and the param is the divisor. As you know, if the divisor is power of 2, we can use logical shift to right instruction instead of division instruction. And it's preferable in terms of execution latency. If the param is a runtime parameter, the compiler can't decide if the parameter is power of 2, so that the compilers always select the division instruction. But JIT can select the most preferable instruction considering runtime conditions. This page only shows the simple example, but we can dynamically optimize our machine code in many other ways. Here is a simple performance comparison. As an example, I choose reduction operation, where the data in an array of size n is accumulated to the variable s. The execution time of the reference code is 23.24 seconds. Of course, we can tune the reference code with the pragma OMP SIMD to use SIMD instructions. In this case, the time is reduced to 6.3 seconds. But if we use Xbyak to generate the instruction sequence to use all the vector registers and optimize instruction order, the execution time becomes 0.45. So Xbyak achieves very good calculation speed. By the way, we have to consider the overhead to generate the machine code sequence dynamically. It depends on the code size we generate. The overhead is about 1 millisecond. So the JIT assembler is useful in applications which create code, JIT code once, and it's used many times. Next, I'll show the environment where Xbyak can operate. This page shows the main development target of Xbyak. We developed Xbyak for the supercomputer Fugak and its derivative systems, FX1000 and 700s. These systems use Fujitsu A64FX CPU, which is designed for high-performance computing and complies with the Armv8 architecture profile and the scalable vector extension. Since Xbyak is written in standard C++, we can use various C++ compilers, such as Fujitsu C++ compiler, GCC, and LLVM. Not only A64FX, but I've tried Xbyak on other platforms. This table shows the proven working configurations. Xbyak AI can run on CPU emulator QM, Apple M1 Mac, and Raspberry Pi. 1DNL is one of the applications that uses all the functionality of Xbyak AI. We confirmed 1DNL works correctly on these platforms, so we can say Xbyak AI works well on this platform. Now, I'll explain how to write code with Xbyak AI. The prototype declaration of mnemonic functions are listed in Xbyak aarch64 mnemonic def.h header file. And the usage samples of mnemonic functions are written in the files of the mnemonic syntax directly. If you want to know how to use a mnemonic function of a particular instruction, you can grep these files. Xbyak AI defines double-reg and X-reg classes for 32-bit and 64-bit general-purpose registers. And Xbyak AI has the instances of these register classes. Of course, you can freely define register instances like the sample A of this page. The generated code will be the same regardless of which register instance you use, like the sample B. Register instances can be made on the fly, like the sample C. Xbyak AI also defines the classes for 128-bit SIMD registers, SVE registers, and predicate registers. Please refer the README file of Xbyak AI. This page shows the general purpose register usage in the procedure called standards for the ARM architecture. If you want to pass parameters to your GTD code and receive a return value from the GTD code, you can construct instruction sequences that comprise with this standard. For example, if you want to pass two 32-bit data to the GTD code, you can assume that the data is stored in the 00 and 11 registers. If you want to receive a single 32-bit data from the GTD code, you can set return value in the 00 register. These methods are the same as the assembly code. The more complex cases are described in the standard. Please refer the document. If you want to many general purpose registers in your GTD code, you can also comply the standards. The standard specifies that the 9th to 15th register can be used freely, and that the 19th to 28th registers should be preserved. Therefore, you can save the 19th to 28th register onto the stack memory at the beginning of your GTD code and restore them at the end of your GTD code. Of course, Xbyak AI supports the branch instructions and jump labels. If you want to make jump labels, please use the label class. If you use the L function, the GTD code address is set to the label instance, and it can be used as an operand of the branch instructions. We can use static table data in GTD code, like this sample. The move instruction sets the table entry address to the X1 register. The add instruction calculates the table element address and set it to the X1 register. The LTR instruction loads the table element from the memory and set it to the 32-bit 00 register. So this example outputs the second element of the table, 0x22222222. We can also generate table dynamically and read it. The DD function writes a single 32-bit value to the digit code memory, and its entry address can be set to a register by using a label and the ADR instruction. And this example also outputs the second element of the table, so output becomes 0x22222222. There are a few points to keep in mind when using Xbyak aarch. The first point is Xbyak aarch can output the instructions that can be executed on the CPU running Xbyak aarch. For example, some CPUs may not support special instructions, such as the cryptographic, atomic, and SPE instructions. But Xbyak aarch running on your CPU can output all machine code of the ARM instruction set, including these instructions. If not supported instructions are executed, the exception of illegal instruction is raised. So please check your CPU capability and choose the mnemonic functions. And the second point is that Xbyak aarch doesn't validate every argument passed to the mnemonic functions. For example, the fmove instruction, which moves a floating value to a register, this instruction is followed by a floating point constant. There is the restriction of the constant value that can be specified as the operand of fmove instruction. If you use a value that can be specified, how Xbyak aarch behaves is undefined. So please be careful to specify the correct value. The operand validation is our future work. Some case, Xbyak aarch checks the operand correctness, but other case, Xbyak aarch doesn't check the correctness. Next, I will discuss debugging methods. At the moment, there is no efficient way to debug JIT code. So basically, it's the same as debugging assembly code. I often use GDB with ASM layout. The JIT code can be dumped as a text file, so it's also helpful to debugging. If you want to debug the JIT code on the GDB, please set a breakpoint to the address of the function pointer f because before it's called. And please set layout to ASM and continue the program execution. Then the program breaks at the start point of JIT code. Once the program breaks, you can step into the JIT code at instruction level with GDB's SI command. And you can also convert the JIT code to a text file to read it. First, write out the JIT code as a binary file. then disassemble it using the object dump command. Then you can get the disassembled code. Let me summarize this talk. I introduced Xbyak aarch64, the just-in-time assembler for ARM instruction sets. Xbyak aarch can dynamically generate optimized code considering runtime parameters and make it easier than the existing assembler to implement optimized code at the instruction level. Xbyak aarch64 is mainly developed to implement the deep learning processing software on the supercomputer Fugak, but it can be expected to work with a variety of software for Armv8 architecture systems. Xbyak aarch is being developed as an open source software. I hope that many people will use Xbyak aarch on various platforms and participate in its development. Questions, bug reports, pull requests, and so on GitHub are very welcome. So please check our GitHub account. And I thank Shigeo Mitsunari. He is the developer of the original Xbyak. He contributed helpful advice to Xbyak aarch64 and brush up our source code. Here is the reference list. Please check our tech blog if you have interested in our software. Thank you for checking my session. That's all. Okay, I have several minutes, so